So let's finish up our discussion of Stokes' theorem. So what does Stokes say? Remember that Stokes says if we are doing an integral, so S is some oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with a positive orientation. The orientation is, for example, if I'm going in this direction in C, then the normals have to point upwards. That's a positive orientation. And then F is a vector field whose components are continuous partial derivatives. Then the line integral along the path, that is sort of like the border of the surface, is equal to the surface integral of the curl of that same vector field. The curl, remember, that is, I think, best remembered by the cross product of the gradient vector with the vector field. So that's how I compute curl. So it's by remembering this formula. That's how you compute a curl. And then the theorem tells you that you can do this switching between line integrals and surface integrals, depending on sometimes one is very easy and one is very hard. So we use this theorem to switch from one to the other. It also has consequences that is telling you something about the how much flow is there. If you think of F as like some fluid dynamics kind of vector field, how much flow there is along the curve is equal to how much flow is there for the curl of F on the surface that is in the surface S. So some examples. We had looked at this example last time. Let me go back to what we did last time for this example. We had looked at this example of a line integral, and what we did is this line integral on a curve that was given like that. It seemed like it was going to be a little bit too complicated, but doing the integral on that surface, which is just the surface z equals 2 minus y on a circle, seemed to be much easier to do. So what we did is, instead of computing the line integral, we used Stokes to compute a surface integral. And we parameterized that surface. We found the tangent directions. We found the cross product of the two. That gives me a perpendicular vector. We verified that if I am going counterclockwise on C, then that is the positive direction of the normal, and that is the normal that we wanted. Then we computed the curl, so the gradient cross product with F, computed the curl, and then we did the integral of the curl, and it turns out we got just pi. Okay. Now, we did some other problem where we had a question that they were asking me to compute the surface integral of curl. And by the way, somebody asked me, well, let me continue. So we were going to compute this integral, and then we used Stokes to, instead of doing the curl integral, we did a line integral. Here, the line that is at the border of this surface is a circle at some height. We computed the height with the square root of 3, and we did that integral. We parameterized that curve that is a circle at height square root of 3, and what we got was that it was 0. And somebody asked me, is that because this vector field is conservative? And the answer is no, because remember that, that vector field is not conservative. We do know that if it's a conservative vector field in a path that is a closed, simple path, we do get 0. But in this case, it's actually not the case. It's not 0 because it's conservative, because in fact, we did compute the curl, and we know that a condition to compute if a vector field is conservative is that the curl has to vanish. But here the curl doesn't vanish, so it cannot be a conservative vector field. In any case, this was one way of doing it. We computed that this integral was 0, so this integral is 0 by Stokes. And then we said, okay, let's do it again, but now I'm going to compute the surface integral. And the surface integral of the curl. I computed the curl. The curl turns out to be this, x minus y, 0, is a non-zero curl, so that means that F is not conservative. And then what we were going to do is, okay, this is sort of like a sphere cap, and we're going to parameterize that, and I was going to parameterize it like this over a circle of radius 1. And then we saw that this is going to be a nightmare because I'm going to have to do the derivative with respect to x of these functions, and the derivative here, there's going to be some square root in a denominator, and then I'm going to have to do a cross product of these. This seems very difficult. And what I finished with in the last lecture is that Stokes is your friend, because if you look at the theorem, at first it just says, the theorem just says I can compute a line integral as a surface integral, as a surface integral as a line integral. But because this integral here does not depend on what surface is on top of that border, it says that I can actually do integrals over whatever surface I want that has that same border and get the same, but not every surface. It has to be, like we said, oriented piecewise smooth surface, and so on. It has to be smooth. But if it has the same border, then the integral is going to be the same. Okay, I can replace this integral, this surface integral, by any other surface as long as the border of S is the same as the border of S prime is that curve C. The surface, the shape of the surface is irrelevant. So what we said is, let's be smart, and instead of integrating over this cap, I'm going to just integrate over a flat circle. That's a surface that has the same border, but it's going to be so much easier to do an integral over, okay? So that's where I'm going to start today. All right, so what I'm going to do is, let's look again at the picture. We have a sphere of radius 2, 1, 2, 1, 2, and then 1, 2, and then here is a square root of 3. Okay, there is, here is the sphere. Okay, and then here is the cap that we're talking about. So the surface S that they describe is within the cylinder and below the sphere. So a priori, the surface that they tell me about looks like this, just exaggerated. It looks like this, okay? But if this is surface S, what I'm saying is that there is another surface that has the same boundary, which is just a flat circle like this. So instead of parametrizing S, we are going to parameterize S1, and Stokes tells me that, so Stokes usually is like a line integral equals a surface integral. But Stokes also can be reinterpreted as the integral over S of the curl of this vector field ds, it turns out is the same as S1 curl of ds. So if they have the same border, then the surface integrals of the curl has to be exactly the same. Okay? So instead of computing this one, which is more difficult, I'm going to compute that one, which is much easier. So we parameterize S1 instead. Okay? So let's parameterize that surface. That surface, again, S1 is given by x squared plus y squared is less or equal to 1, and z is exactly a square root of 3. So, so this curve is going to be I can parameterize it, and I can do a parameterization of this. We could do just something like, well, as easy as u v square root of 3, and the domain is precisely points x, y that are in the unit circle, right? And then I have to find the normal vector. But the normal vector to this, so what I would compute is RU, RV, and then their cross product, right? But I don't need to go through that length because I'm just finding a normal vector to a surface which is flat, parallel to the xy plane. So I know a normal vector here. What is that normal vector? The normal vector is just the vector 0, 0, 1. And if I'm parameterizing my curve in that direction, which is what I should be doing, then that is the normal in the positively oriented direction. And if you actually go through the process of computing this cross product, do the derivative, the cross product, you'll see that you do have that normal vector. Okay? You do get that normal vector of the cross product. When you do the cross product, the RU will be 1, 0, 0, RV will be 0, 1, 0. Do the cross product of that, ij, k with those two vectors, you get 0, 0, 1. Okay? So I have my normal vector. Now I need the curl. So what is the curl of f? The curl of f is this, and I can compute that also. And let me just say that that is x minus y 0 is the curl. Okay. And now I would have to parameterize this curl. So I would do this evaluated at the parameterization. Okay, but the parameterization had u, v, comma, square root of 3. This is the parameterization is right here. Is u, v, square root of 3. So the parameterization is just u minus v, 0. And remember that to do the integral ds, what I actually do is doing the integral over the domain of the cross product evaluated at the parameterization and dot the normal vector. And for normal, I get 0, 0, 1, dA. But when I do the dot product of this, what I got here, which was something, 0, dot with 0, 0, 1, I get a fat 0 for that function. The dot product of the two things is 0. So this is the integral over the domain of 0 dA, which is just 0. Which is what we got in the other interpretation, in the other last time. We did this by actually computing the line integral over the border, and that also gave us 0. But not because f was conservative, just because it was 0. Okay, let's do another one. This time I want to compute the curl of this complicated vector field, and S is a semi-sphere. X squared plus y squared plus z squared equals 9 over z bigger or equal to 0 and oriented upwards. Okay, so what am I going to do? So what we can do instead is we're going to parameterize So this tells me that let's draw first what's happening here. This is a semi-sphere of radius 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it looks like this. Okay. So that is the surface, and it is oriented upwards. So here are my normals. Okay. The path is going to be a circle. Okay. The path that is at the border is a circle of radius 3. And now how I am going to compute this, this is again, it seems to be going to be very complicated to compute the curl of this thing. So instead of computing the curl, I'm going to try to just compute the line integral about the curve. Okay, so again, I'm going to use Stokes to say that the integral over the surface of the curl of f ds, this has to be the integral about the path c of f dr. The line integral over a closed path, positively oriented path, like that. Okay. So first of all, what is this path? This path corresponds to, well, the path is the line x squared plus y squared plus z squared equals 9 with z equals 0. So that is the x squared plus y squared equals 9. So it is a circle of radius 3. Okay. And let's see if I actually need to do all the work of parameterizing this circle. For now, I'm not going to parameterize it. I'm just going to see what is the vector field when I am on points in this path. These points, whatever they are going to be something, something, and 0, right? The points are all in the xy plane, so they have a 0 coordinate. So whatever they are, the vector field evaluated at points on the path, the z coordinate is going to become 0. So if the vector field was 2y cosine z e to the x sine z x times e to the y, when I evaluate with z equals 0, this simplifies to cosine of 0 is 1, so this is 2y. Sine of 0 is 0, so this is 0. And then I have an x e to the y over here. Okay, so you can see why we would want to just do an integral over this path, because, well, it does simplify quite a bit to do it over the path. This vector field on that path is a lot simpler. Let me now, what I want to do is the line integral over the path of this. Dr is dx, dy, and 0, because we're just in the xy plane. And when I do f dr, if I do the dot product of f with dr, so the f dr is 2y 0 x e to the y dot this dx dy 0. So what I get in total is the 2y dx. So that is the integral that I'm trying to do, is the integral over this path of 2y dx. Now, to do that integral, now I still haven't parameterized my line, or my circle of radius 3, and I can do that, but I can also now use Green's theorem, because this is a circle of radius 3. So now if I'm just looking at the xy plane, I have a path here up to 3. And Green's now tells me that instead of doing this path over here, I can switch for an area integral over the inside. So now, remember what Green's tells you. So Green's now tells you that the integral of p dx plus q dy, that is the double integral of delta, or the partial of q with respect to x minus the partial of p with respect to y dA. Okay, and that integral we have in our case p is 2y and q is just 0. So when I do the switch using Green's, that will be the integral over the disk, not over, so if inside I have the disk of the derivative of q with respect to x, which is 0, minus the derivative of p with respect to y, which is 2, the area. And now that's great because that is just the integral over the disk of, let me take the minus 2 out, minus 2 integral over the disk of dA, or 1 times dA, and that is the integral of 1 dA over the disk is the area of the disk, which is 9 pi. So this answer here will be minus 2 times 9 pi, so it is minus 18 pi. So that's the answer.
Did you use Green's and Stokes?
Yes, yes. We did a double theorem here where I was using, first, they are asking me to compute the integral of a curl. I use Stokes here. Let's give a Stokes a different color here. So here is Stokes. That's not a great color, but that is where I'm using a Stokes to switch the surface area for a line integral, and then I'm switching the line integral for a area integral, which is in fact, we're going to try to do this again. What I could have done, let's not do it again, but what I could have done is do the same thing I did before. Instead of doing this curl over, instead of doing the curl over this surface, I could have switched by the surface that is just the disk of radius 3 and do the integral of surface in that one. For that one, though, you still have to compute the curl and then parameterize there. So it's still a little complicated, more complicated than it needs to be, because you still have to compute the curl and then evaluate. But by doing this, of first switching with the Stokes to a line integral and then using Green's to switch from a line integral to an area integral, I didn't have to do almost any work. Yeah. If you wanted to do this one, yes. So we could, I don't have the room right here, but I could have done this one, which is this integral right here. So this one I could have done, take f, which I have, this is f, parameterize the circle of radius 3, so 3 cosine t, 3 sine t, comma 0, right? And then do the dot product of this with the circle. When I do that, that's why sort of like there is a 0 here. That's what's dx, dy in there, because when I do that, what did I say? The parameterization was going to be 3 cosine t, 3 sine t, comma 0. If I evaluate at my vector field at the path, I'm going to get something in here, but then when I dot with the derivative of the path, there's not going to be z component. There is no dz in the resulting line integral. Okay, this line integral is really still a line integral in space. It's a 3D line integral, but it becomes a plane line integral essentially because of what's happening. If you want, we can come back to that after, if we could just do it. Do you want to do it? You want to see it? I don't want to put you in the spot. Well, if you want, we can come back to it later. Yes.
I'm good with the product.
Yeah, that would have worked. In here, I didn't need to use Green's theorem. I'm just using Green's theorem to add in that I'm just trying both out at the same time. But I could have just done this one, okay? I could have just done the integral of FDR by parameterizing the curve and then doing what it was mentioned, the F evaluated at R times R prime T, and then do that integral. Let's do that. Okay, so I do have a little space here. We're trying to do the integral of f dr, where f, I believe it was 2y0 x e to the y. In the circle is this circle. Okay, so we can parameterize C. Parameterization, a nice parameterization is 3 cosine t, 3 sine t, comma 0, because I want to parameterize it. This is with C equals 0. It's a 3D curve, right? But it's just in the xy plane. So I parameterize it in space like that. In that viewing from above, that parameterization is positively oriented because it's going counterclockwise. So that is a good one. I'm going to evaluate R prime. That is minus 3 sine t, 3 cosine t, comma 0. Then take f and evaluate it at R of t. That is 2y, so 2, so it's 6 sine of t, then 0, and then this is 3 cosine t e to the 3 sine t, right? And now I have to do f r of t dot with the tangent vector, with r prime t. And when I do that, what I get, it just minus 3 times 6, so minus 18, and sine the square of t. 0, whoops, no, this is just already a dot product, so I get plus 0 plus 0. It's minus 18 sine square t. Okay? And now the integral of f dr becomes the integral in what interval are we integrating? This is going from 0 to 2 pi. So it's from 0 to 2 pi of minus 18 sine square of t dt. And this is minus 18 integral from 0 to 2 pi of sine square of t dt. And that's one of those that the integral of that function is equal to pi. So this is minus 18 pi. Just like before. If there was a z component, this would work. It would just like the dot product would be a little bit more complicated, but it would just be a line integral.
I'm saying through Stokes, you just turn it into this anyway.
Oh, yeah, you can still, I mean, you can, through Stokes, what you can do is this integral over here, you can make it into a line integral of whatever the border curve is. And in here, just the border happened to be in the xy plane. But this border could have been tilted, right? It could have been a half sphere that's sort of like tilted, and this line could have been a complicated line to parameterize. Okay? Right. The last example I wanted to show you is this one. So in this one, we are integrating the curl of f This is the same vector field that we had in the previous example, but now I have a different surface. The surface is now, there is a cylinder of radius 3 still, but now this is a cylinder like this, okay, up to z equals 4, together with the top, so it is this surface. So the top is included and the sides, but not the bottom, okay? What this means is that the curve at the bottom, the border of the surface, it's still the same curve we had before, x squared plus y squared equals 9 with z equals 0, okay? So I've just switched a surface. So if this was, if they're telling me to do the integral over s of the curl of f ds, I can switch. I can switch first via our friend Stokes. I can switch to the one we just did. I can switch to the hemisphere. Okay, so this is S, this was S prime, and this is the same as if I do the curl over S prime. But I already did that. This was also the integral over a curve FDR, and that's how we compute it either in one way or the other, or we used greens and further to compute this. But in any way, we already computed this, and this was minus 18 pi. Okay? I could have also, if somehow it was convenient, I could have also used Stokes to replace this by simply the surface that is just the flat disk in the xy plane. Okay, I guess the surfaces are in green, so it could have been switched by this S double prime if I wanted to, and compute there. So that's the power of Stokes, that not only is telling you you can convert surface integrals to a line integral, you can also switch from surface to surface, and the answer is going to be the same. And this is computed. If you go in the book, there are some applications of this in physics, where you have problems about electromagnetic fields in complicated surfaces. And to compute those, what you do is you replace the surface by another surface where it's easy to compute instead of like some crazy-looking surface. So that's a good point. So we still need a orientation. And the orientation is that when we do these integrals, if you're integrating this one, which is, if say we're parameterizing the curve, the surface, that one was awful over here. If we are parameterizing, oh geez, the surface, so the normals are there, then you have to do your line integral in this direction. It has to be parameterized in that direction. So when we did the line integral, that mattered in that our line integral here, I parameterized my curve in this direction, which is the positive oriented direction. Had I parameterized in the opposite direction, then I would have probably gotten an 18 pi instead of a minus 18 pi, which is not the actual surface integral. So you have to parameterize in the curve and the surface have to be parameterized. You're doing integrals with respect to a normal and one with respect to an orientation of the curve that match their orientations in the positive direction. Well, here you are asked to evaluate the surface integral, and you have to figure out how to do that. You can just evaluate that directly if you can, or in this case, what we did is replace the surface integral by a line integral that it was easier to compute.
So you know it's a Stokes problem if you start out with double integral over curl?
for sure, if that's a big clue that if they're telling you do the double integral of a curl, then that's automatically you're in the setup of Stokes. Sometimes you might find they might give you a function, and then you have to identify, is that a curl? That would be a little bit more complicated, but sometimes you can figure out like, okay, that function is the curl of a vector field, so I'm going to replace by that vector field. We did this in the fundamental theorem of line integrals, where we realized that if we're doing the integral of a conservative vector field, then it's going to be 0. So we were trying to figure out, is this vector field the gradient of another function? So we did that sort of maneuvering in some other cases. So in here, but yes, if the integral that they give you is already in the form of a curl, that's a big hint that you should try to use Stokes in between.